Hello, everyone. Welcome to another session of the Data Science Mentor cohort. My name is Pablo. I am a data science professional. I'm the founder, the convener, and the host of the Data Science Mentor program. And today we are starting off with deep dives into um, supervised machine learning techniques and unsupervised machine learning techniques. And today we are looking at the naive bias classification. Um, this is an algorithm that is inspired by probability. And in the part one of this, we are going to we're going to take step by step. We're going to take steps to understand this algorithm intuitively. We are not, I'll try as much as I can not to, share a lot of technical jargon, but what I'll try to do is explain it intuitively before we get into writing code, because we need to understand how it connects to reality, the real world use case. All right. The data science mentor cohort helps anyone starting data science from scratch, building your data science skills as you move towards machine learning and any other advanced related um, technique or technology associated with that. So let's get started. Now, we are the thing about the naive um, Bayes. It's actually the naive Bayes classification, not bias, but the naive Bayes classification is we're going to look at a few things. As I will do, I will share this. I'll share bullet points as we we look at as we look at this. Now, there are a group of models. They're called the naive Bayes classification, naive Bayes models, and there are they are fundamentally using the Bayes theory, right? And we're going to look at this one, right? So what exactly is a Bayesian classification? Right. I know when I started out first, I called it a bias, but most times I'm always like, you always hear people say Bayesian, you have Bayesian and all that, but I'll like jump between Bayesian and Bayesian, but I think sometimes Bayesian just works really well. All right. So this first off, we're going to look at this. So this is a supervised ML technique. Is a supervised ML algorithm. That's one. It's a supervised ML algorithm, right? Now, naive Bayes models are extremely fast, and this Bayes model, they're fast and simple classification algorithms, right? So that's what they are. They are fast and simple. Fast and simple classification algorithms. That's one. Another thing is they're suitable for data sets that are have they're like loads and loads of data, loads of dimensions in them, right? When we talked about when we talk about dimensionality reduction, we're talking about high dimensional data that has a lot of you know that has a lot to it, right? And so it's suitable for that. And they have very few parameters, so they're really quick and useful stuff. So they're fast and simple. Yeah, you typically can use them for your, what's the term? Um, there's a term for it. You can use it for your benchmark or your baseline stuff. So another thing we're going to say is they have few tunable parameters. Yeah, they're fast, simple, have few tunable parameters. Yeah, so and which also makes them good for building baselines. Now, at this point, I'm saying really, really big. I'm speaking like technical jargons, right? So what I'm going to do is I'm going to get into the intuitive mode. So this is one. So let's get here. Now, next I'm going to do is I am now going to talk about the Bayes, this the Bayes algorithm, the naive Bayes algorithm, but I'm going to now make it intuitive. So here I'm going to call this the naive Bayes algorithm. And then in brackets, I'm going to write intuitive. So here, I'll talk about it, but there will be no, I won't be talking about stuff like maybe tunable parameters and stuff. So yes, so before I come here, let me come over here and say this, right? Naive Bayes models are inspired by probability, right? So they're inspired by probability. So at any point I'll come over here. I'm going to, let me call this one technical. This is going to be our technical bit. Yeah, that's what this is. And then this is going to be our intuitive bit. So we're going to jump into in between the technical and the intuitive bit. Now let's imagine you're a doctor and you are diagnosing a patient that has flu. So this is going to be our steps. These are the steps we're going to use. So we assume you are a doctor, right? And you have a job. You are diagnosing you're diagnosing a patient. You're diagnosing a patient. You're diagnosing a patient, and you're diagnosing a patient. You're diagnosing a patient. Or let me put this way: you're diagnosing whether a patient has flu. Has flu. Now, at this point, since it's you can now see at this point, since it's a classification model, the target label, which is what we are predicting, is discrete. So does the patient have flu or not? So this is what we're going to do. So what we are trying to do, right, is to ask the question, does the patient have flu or not? That's it. I wonder why I'm spelling the flu with an E. Does patient have flu or not? Now, to do this, you're going to look at symptoms. So we have to look at symptoms. Mind you, these symptoms is there are explanatory variables. You see? So that's the intuitive way of looking at it. These symptoms are the explanatory variables that gives us a clue if there's flu or not. Right? So we're going to look at these symptoms. So now, what are these symptoms? These symptoms could be cough, it could be fever, it could be runny nose. What are other features? What are other symptoms of a flu? So let's look at cough, fever, runny nose, and all that. And let's say headache. Right. So these are the symptoms. Right. Now, the next question that, so with the Bayes, with the Bayes, with Naive-Bayes classification algorithm, right? We want to combine these symptoms to make a prediction. So here we will combine these symptoms, or combine these symptoms, or rather, not yes, these are like symptoms, right? And these symptoms are like clues. So we'll combine these symptoms to make a prediction. And remember what the prediction is. The prediction is, does the patient have flu or not? In fact, there is even a nicer way to look at it. So we're going to look at it this way and say, given these symptoms, what's the probability? What's the probability that what's the probability this patient has flu? So this is, for lack of a better term, this is basically like the Naive-Bayes workflow in terms of what we're trying to do, the thought process, the thought flow on it. So this is the intuitive. This is an intuitive way of thinking about the Naive-Bayes algorithm, right? So that's for now. If you were looking at it from a technical perspective, right? Let me come back to this technical side of things, and then we can push this, right? Now in the technical side of things, we would write a lot of technical statements, right? So here I would say Naive-Bayes. Naive-Bayes uses an equation describing the relationship of conditional probabilities. So Naive-Bayes is an equation. Describing the relationship of conditional probabilities. The relationship of conditional probabilities. Now, do you see that? This is some technical stuff. But when I come down here, is given these symptoms, what's the probability this patient has flu? You can see the difference in that conversation. Right. So that's whenever you have a situation like this, that you are basically saying, given certain economic activities, what's the probability that the people in this economy are doing, or poor or are middle class, right? And so these are the kind of things, that's what naive Bayes does in machine learning. It uses probabilities to classify things, right? So this is what we're trying to do. So we use the probabilities that that this patient has cough, fever, runny nose, headache, to to classify if the patient has flu or not, right? So this is what it is. Now, again, every machine learning algorithm has assumptions. So the naive Bayes has assumptions. A very good example is the linear regression. The linear regression has an assumption that the data distribution in the explanatory variables, or the clues or the symptoms, have a linear relationship. So in this case, if it's a linear relationship, we're looking for what's the linear that does the likelihood of, if someone has a high fever, is that a higher chance that the person has flu? But so these are this. Now there is also the Bayes theory, or almost always has an assumption that the existence of a clue is an indication that something might happen, or the existence of a clue in the past is an indication of the possibility of something happening in the future. It's if I was to take it a little like an extreme and say what the existence, if there's been if there's been a relationship, if there's a relationship between a man and a woman, is there the fact that there's infidelity is a thing, means there is a conditional possibility that it might happen in the future. The question is, where does it fall in the probability scale? That's basically that. If businesses have collapsed in the past, then there's a huge possibility that the business being created today will collapse in future. The question is, what are the possibilities that it will? Now you now have an algorithm that helps you, that puts a quantity to that. What's the quantity? What's the probability that puts like a numerical representation to the possibility that that will happen? That's typically what and that's typically what it is. A lot of the medical professionals use it a lot, but they use it even when they're tested, when they're looking at their patients. And that maybe that's the reason why I am using this as an explanation here. Now, the next thing we're going to do is to look at the assumptions. And it's important for us to look at these assumptions, because these assumptions will eventually help us make sense of it will help us make sense of a lot of things. All right. So here, let's look at assumptions. So the assumptions behind the assumption behind naive Bayes, the naive Bayes algorithm, the assumption behind the naive Bayes. Now, let's look at a few assumptions. And let me put this here. Now, one assumption is all the features, which are the symptoms here, are independent of each other. So here, all the features, and if we're talking about the illness we're looking at here, say all the features, say the cough, the fever, the fever, the runny nose, all this are independent of each other. Right. So it assumes that if you're having a fever and having a cough, that they're separate. Even though in real life they are related, it's that it's these are the things that they are all independent of each other. Right. So it's, you know, so that's one. Also, the second one is that it also says that how do I look at this? I mentioned it earlier on that, for instance, it's like a question that says, how likely is that the information we have belongs to like the information we have is, does this person have flu? So the just like I mentioned when we were just like I mentioned earlier, the conditional probabilities, right, of something that has happened in the past, right? So it's there's an assumption that given what we know, what is the possibility that this has happened or this is possible? So it has an assumption that given what we know. So what do we know about flu? Right? Given what we know, flu, how likely are the features? How likely are the features? How likely are these features, or how likely are these features belonging? Look at the English that I'm speaking. How likely are how likely are these features belonging to the flu class, belonging to the class, right? Now, when we say the class, we're talking about the class of flu or not. So this is it. Given what we know, which is the flu, how likely are these features belonging to the class? Like how likely are these features? How likely do again, you could just get it. So I'm not a master in the English thing, but how likely are these features belonging to the class, flu or not? Right. Look at this. These are like assumptions because this is what we're looking at. So if we have situations where we say, what are the chances that a business will stay up 5 years? And now you want to know, given what we know about how businesses fail, how likely do we look at the features, right, that this business has now that it belongs to the classes of business that fail in 5 years? So this is basically what it is. Now, these are used in real life to do a lot of things. Again, emails, spam detection, right? Looking at words, certain words in a spam. What are the chances that, has this word been in spams before? And there's a higher chance it could be. There's a chance it could also be in the email we're seeing. You can also review tweets, say, given that certain tweets contain certain negative words, what's the chance that this could be a hate speech, right? So that's why typically you could write, you could see people on the social media trying to avoid certain terms so that they don't get classified as maybe hate speech or fail the community policy, right? Given certain symptoms, exactly what I'm talking about, like classify whether a patient has a certain disease or not. And then given that these symptoms have been there in the past, there's a chance that this person would have that. So these are basically these are like typically what the assumption is. So the final part of it is we need to explore our data before modeling, which is a huge, this is part of what data scientists do. So here, exploring our data before modeling, right? Now here, when this is being put up, right? What we are now saying here is what are the things we're going to do in this situation. Now, first things first, if we're going to explore our data before modeling, we will check for the following. We would check for class distribution, right? So here we will check for class distribution. Now, in this situation, we're interested in, look, are the classes we are trying to predict, are they balanced? So here we're asking, are classes balanced? So here, so that we don't get into that technical jargon area, what it means here is if we are going to predict flu or not, the existing data we have, the flu or not class, are they balanced? Because it's important that they are balanced, because if at any point they seem not balanced, there are chances that the algorithm will say, look, we see this a lot today. What the chances are that it is this? But another thing is we have to also feature importance is a thing. What's feature importance here? For instance, if you're talking about flu, what are those important symptoms we're looking at? So those things are really, so we have to do our analysis to know how important these features are. It's a huge thing, right? We have to handle missing values. We must handle missing values, right? And because with this algorithm can handle missing values on its own, so it's important. And then we have to encode our categorical features. So that means we have to convert our categorical features. And when we say categorical features, we mean features that are not numbers. We have to do that. So yeah, so these are the things you would typically want to do if we are starting out with the naive Bayes classification, right? These are the things we are going to do. Now, this is the first part of it, right? In the second part of what we're doing, we are going to basically look at the different flavors. We're basically going to look at the different flavors. We're going to look at different flavors we have, visualize them, and go on to do and the ones that even make a lot of sense is when we do some form of a text classification, because that's one thing we want to do. A huge example is text classification, where we fetch texts and then try and find out how we can classify these texts, right? So yeah, we're going to do that. So this is just the first part. I want us to always realize that in the first part, there's a lot of explanation that happens, right? And it's ideal to understand all this. And if we make sense of it, then the next step is to build on that. Always remember it's important we do that. All right, guys. So that's that. If you're watching this session, it means you're live in our live session. So feel free to ask any questions. If you are watching the recorded session, then please feel free to drop a question in the Telegram channel, right? And if by a stroke of luck we streamed this live, drop a question in the comment section